Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, last time we have completed the point the charge transfer spectra, and today we are going to see this Nephelauxetic effect. When the metal ion is in gaseous state and isolated state, the electron cloud of that metal ion is limited to certain space, and the electrons pairing takes place within that space. But if the metal ion enters into a complex by formation of bonds with ligands, the atomic orbitals of donor atom of ligands are pointing in the direction of metal ion, and this increases or adds together the orbitals of ligands, that is donor atom and the metal ion, and it provides the larger space for the electrons of metal ion to undergo pairing, and the pairing is becoming very easy. Means the effectiveness of pairing becomes very easy in a complexer metal than that is possible in case of isolated gaseous metal ion. This is because the metal ion has limited space around the metal ion, and after the formation of complex, the space around the metal ion is increased because the ligand atomic orbitals are also pointing in this direction of the metal ion. So this improves the effectiveness of pairing, means pairing of electrons becomes more easy in the complex rather than that is possible in case of metal ion. If we see the complex consequences, as we have discussed here, that the space is increased, etc. We have seen this. For example, if we consider the ligands such as Cl minus, so these ligands are showing complex bond formation, means the pi bonding with metal ion, and this improves the larger space for the electrons for undergoing pairing. So the force required for pairing of electrons in this larger space is very less, or it is less rather than it is available in the isolated gaseous metal ion. So this effect is called Nephelauxetic effect, and this is possible, means the effect is increasing when the ligands are softer and softer, means the harder ligands do not have the atomic orbitals pointing in the direction of metal ion. As a result of this, the contribution of ligands to the Nephelauxetic effect is less, and therefore the magnitude of Nephelauxetic effect is less here, because it requires, means in such complex where the ligands are relatively harder, the Nephelauxetic effect is smaller, and therefore the energy required for forcing the electrons for pairing is more here. But in case of softer ligands, the energy, the Nephelauxetic effect is enhanced because the ligands are softer, larger in size. They can be easily polarized, means the electron cloud of ligand is more polarized towards metal ion. So the ligands such as I minus, then this Cl minus, etc. have these electrons. Say this is the metal and these are the ligands. So the electron cloud is pointing towards this metal ion larger. Because of this, the covalent bonding, the covalency of the bonding, covalency of the bonding increases. The bond becomes more covalent. So this is possible only when the ligand is softer. So these are soft ligands. So more softness of these ligands increases the Nephelauxetic effect, and the covalency of the bond, metal ligand bond, also increases. But if the metal ligand bond is formed where the ligand is harder, the covalency is weaker. The metal ligand bonds are less covalent, means they are more ionic in nature. So the antibonding orbitals of this Cn minus have also matching symmetry orbitals with the metal ion. If this is Cn minus, the carbon has antibonding pi orbitals, and metal ion has also pi symmetry orbitals, and therefore the pi bonds are easily formed. The Raka parameters, can be given for the metal ions as well as these ligands. So for ligands, the Raka parameters, I will show here metal ion in gaseous nature. So it has this Raka parameter, called B, and the Raka parameter for metal ligand so this metal is called B prime. So B is the Raka parameter for metal ion in gaseous state, while B prime is called the Raka parameter for this metal ion which is in complex state, that is for complex ion, complex metal. The Nephelauxetic ratio, we can get the Nephelauxetic ratio as beta. Nephelauxetic ratio, that is beta. So beta is equal to this beta prime upon B prime upon B. So this gives the ratio. So this value beta expresses the Nephelauxetic ratio. You should know that the beta and B and C are the Raka parameters for a metal ion, and these are variables whose exact values depend on the nature of ligands attached to the metal ion. Now from this Raka parameters, the C.K. Jorgensen Sun divides the relation for Nephelauxetic effect. Give relation for this Nephelauxetic effect. And for this purpose he used the two symbols, that is the parameter characteristic of the ligand. So this Nephelauxetic effect is a product of the parameter characteristic of the ligand and parameter characteristic of the metal ion. So here the relation is, that is 1 minus beta is equal to H into K. Now here this H is the parameter for ligand and K is parameter for metal ion. And from this we can get this mathematical equation, and after substituting for beta, the equation becomes after substituting for beta, the equation becomes beta prime only b prime is equal to b minus BHK, B minus BHK. So from this equation, the Raka parameter for metal ion in a complex B prime is the value of gaseous ion reduced by correction. The Clausen expanding effect shows that the effect is a function of nature of metal ion and nature of ligand. Now, what is the nature of metal ion and nature of ligand? The metal ion and ligands nature is considered in terms of hardness or softness. When the metal ions are harder, metal ion is hard. So the harder metal ion is small in size and high charge, whereas the softer ligand or stronger or larger Nephelauxetic effect, we require metal ion hard and ligand soft. So softer ligands are larger in size. And they can be easily polarizable. They can be easily polarized. So easily polarized. So we can have the example of the I minus. If we see the halides, F minus is smallest in size, so it is harder. Then Cl minus is relatively larger in size, so it is compared to F minus, it is more. So the order of these halides is given in this way. So F minus Cl minus, Dr minus, I minus. So this is hard and this is soft. So hardness decrease in this direction or softness increase. Nephelauxetic effect can also be calculated using the spectral data. Spectral data is also important in order to calculate the Nephelauxetic effect, that is cloud expanding effect, and from which we can find out how much there is reduction in inter-electron repulsion between the electrons of metal ion that can be forced to pairing. Spectral data provides us lowest energy absorption band, from which we can calculate the delta value, that is crystal field splitting energy, as well as we can find the beta value, and also we can get the reduction, that is the value of reduction in inter-electron repulsion. In other words, we can say it will tell us how much it is easy to force the electrons for pairing in the complex because of the Nephelauxetic effect. So data show in the spectral observations provides us valuable information. The softer ligands are N3 azide, that is N3 minus, Br minus, Cl minus, etc. So we will see this data in the table also. So it will help us, that means softer the ligand, the degree of covalency is larger when metal ion is bonded with such softer ligand, because the delocalization of electrons becomes very easy in case of larger region in space that is available for delocalization of electrons of metal ion. But if the metal ion is in the gaseous state, the space is limited and that is not larger enough to undergo easy pairing of electrons. So it also shows that the metal ion with high charge, we have shown here that the metal ion with high charge and small size is also necessary for effective Nephelauxetic effect. So hardness and softness plays important role in the Nephelauxetic effects. Now we will show this in the tabular form and how to calculate the Nephelauxetic effect or reduction in energy that is required for pairing. We can show these metal ions Mn plus, then their K values, then ligands and their H values. Now you will show here that is first metal ion is Mn2 plus. It has 0.07 K value. Then vanadium V2 plus. It has 0.1 Ni2 plus. It has 0.12 molybdenum 3 plus 0.50. Then chromium 3 plus, it has 0.20. Then Fe3 plus 0.24. RH 3 plus 0.28. Then IR 3 plus 0.28. Cobalt 3 plus 0.33. Mn 4 plus 0.5. Pt4 plus 0.6. Pd 4 plus 0.7 and Ni4 plus 0.8. Similarly, we can have the values for gas. So the ligand is F minus having 0.7, 0.8. Then H2O has 1.0. Then CH3 twice, that is Me, we can say Me and CHO 1.2. NH3 has value 1.4. Ethylene diamine 1.5. Oxalato 2 minus 1.5. Cl minus 2.0. Cl minus 2.1. Br minus 2.3. N3 as N3 minus 2.4. I minus 2.7. So you can watch this table, that is metal ion and ligands. So the K values are Kataka parameters for these metal ions and H values for ligands. So if we observe this, you will find that your K values are increasing in this direction. The H values are also increasing in this direction. So hardness increases in this direction and softness increases in this direction. So we generally represent this that this shows increasing Nephelauxetic effect or cloud expanding effect. Increasing Nephelauxetic effect in this direction for both metal ions and ligands. So this is for both. You have to remember, this is not only for ligands. We have shown that the hardness will show here the eta. Eta means hardness. Will show here hardness. Hardness increases in this direction and softness increases in this direction. So both values together help the Nephelauxetic effect, that is cloud expanding effect, and it shows reduction in the energy for pairing. We can show the calculation how the reduction in energy for pairing because of the cloud expanding or Nephelauxetic effect. We will take the example of Fe reduction, percentage reduction in decrease or reduction, percentage reduction in energy for Nephelauxetic effect, pairing energy. Now I will take this example of FeF6 3 minus. FeF6 3 minus. So here from this our data, from this table, we can have the relation, that is beta minus B minus B upon B is equal to H for ligand minus into K for metal ions. So we have shown these H for ligand, K for metal ion. Now if we substitute these values, then we can get so for Fe the K value is 0.07. 0.07 into the F value is 0.8. So from this we can get Fe. We are taking Fe, not Mn here. We have to consider this value and this value. So for here we get this 0.24 we can take, or 0.8 into 0.24. So this gives us 0.192. 192. So here you will find that if the metal ion, so these values are in gaseous state, metal ion in gaseous state. So the 100% energy required is 0.24, and this is so we can calculate this difference in energy. So this is 100%, means 0.24 is 100%. Therefore, this is 0.192 is how much we can calculate here. 0.192 upon 0.24 into 100. So this will give us 15%. So there is 19% reduction in energy required for pairing, and this depends upon the nature of metal and nature of ligand. Now we will see how to calculate this reduction in energy by using spectral data. So calculation of delta or dq and beta for octahedral complex of for Ni2 complex that is Me2 SO4 2 ClO4 2. So this is D8 metal ion. This is D8 metal ion, D8 configuration. Here we know that the D and beta values we have already seen. The B parameter, Raka parameter for ligands, and the Raka parameter for metal ion is B prime. So from this we can get beta. So we can have this beta is equal to B upon B prime, and we can have this beta 0 is equal to 1 minus B beta into 100. So using these relations we can find the value for B is 1056 per centimeter, and the nickel 2 plus complex, this complex has three bands, absorption bands. These are the values are at 7728, 1297 and 24,038 per centimeter. So the value of delta is estimated directly from lower energy transition. Because lower energy transition is A1 A2G 2 means triplet A2G to triplet T2G F. So this value is, our energy is this 7000, this is 7728 per centimeter. So from this, so this is the dq. So this is equal to, this value is equal to 10 dq. 10 dq. Therefore, dq is equal to 773 per centimeter. Now the value for beta prime b prime is obtained by substituting for dq, that is equal to 773 per centimeter in equation. This square is equal to square minus 6 dq plus 15 b prime into e plus 90 dq into b prime minus 16 dq square is equal to 0. So we are having the dq values, then its b values, so from which we can calculate the beta prime. So it gives beta is equal to b prime is equal to 921 per centimeter. Then we can get this beta, that is b upon b prime. This is equal to 773 upon 921, and it is 0.872. Then beta is equal to this beta 0 is equal to 1 minus beta into 100. So this beta value is used here, and it shows that 1 minus 0.872 into 100. This is equal to 0.128 into 100, and this is equal to 12.8%. So when the complex is formed, the reduction in the energy required for creating or pairing electrons is reduced. That is, we have calculated the reduction, reduced by 12.8%. So in this way, the reduction in energy for pairing the electrons due to Nephelauxetic effect is calculated using the spectral data also. So with this we have completed this point as well as this topic, and next time we are going to begin with new topic, that is metal carbonyls and related compounds. So we will stop our discussion here. Please subscribe to this channel and also press the like button and bell icon also, and you can put your comments in the comment box, so that it is possible for us to improve the things in future. So thank you very much for watching it.